All right, so let's take a look here. This is what we went over yesterday. Okay, so we went through a bunch of different power functions, and we figured out that if it was x to an even power, it started up here and ended up here. And the bigger the number got, the steeper it got on the outside and the flatter it got in the middle. And we even looked at like x to the 100th. And x to the 100th basically came down, kind of went like that, and then went almost straight back up. Had a really sharp curve here. And if it was x to an odd power, it starts down here and ends up here. So x to the third looks like that, x to the fifth, little steeper here, flatter in the middle, and we graphed x to the 99th, and x to the 99th did something like this. Okay, remember those? And then what we did is we looked at a couple little transformations. So a little vertical flip, take x to the fourth, reflect it across the x-axis, then stretch it by a factor of 3. Still opens down, still really steep outside, and then really flat in the middle. Negative 2x to the fifth. Instead of starting down here and going up, it's going to start up here and go down. Really steep, flat in the middle, and so forth. And we even talked about how you could take a linear function like y equals x, vertically flip it with the negative, vertically stretch it with the 2 so it's a steep line going in the negative direction, starting up here and ending down there, and then slide it up one to get that particular graph. Okay? And then we ran through a bunch of vocabulary words. We talked about what a power function was. Okay? X raised to a number. And if we put a 4 in front, all that does is vertically stretch the power function. And we talked about what its degree is. Its degree is the power. It's the exponent. And if we put them together to make a polynomial, like this is a polynomial, then the degree isn't what we get when we add all the powers up. It's not the degree of each term added together. It's just the biggest one. It's the highest power. So this is degree 4. That's degree 4, that's degree 8. And we said it's going to have the behavior, or it's going to resemble, or it's going to look like the highest power. Okay? So this one right here would look like negative 3x to the 4th. This one would look like 5x to the 8th. Okay? And then we talked about what it means to be a 0. It means when you plug it in, you get out a 0. It's not that we plug a 0 in, it's that we get out a 0. And we said if we have a 0, then we know what one of the factors is. So if r is a 0, then x minus r is a factor. And we kind of use those things interchangeably. And we also talked about the fact that if we're saying 0, we could also call that an x-intercept or a solution. It's also called a root sometimes. And then we had this little example where we had a factored function where we had this factor, this factor, this factor, and this factor. So we had 4 factors altogether, and each one of them produced a 0. So the one that comes from here is positive 5/2. The one that comes from here is negative 3. The one that comes from here is negative 2. And the one that comes from here, and for some reason this messes people up, the x-intercept or the 0 that comes from there is 0. So what would make this one 0? What would make this one 0? What would make this one 0? And what would make that one 0? And then we went through and we said, well, wait a minute. If you multiplied all these x's together, just the x times the x times the x times the 2x, you get 2x to the 4th. And that will tell you what it behaves like. So that means it starts up here and ends up here. Might wiggle around in between, and we call those turning points, and we'll review those again in just a second. So this one's got to cross at 0. It's got to cross at 2, at 2.5, and at negative 3. And if it starts up here, it crosses through, crosses through, crosses through, and looks something like that. So it doesn't just flatten out, it actually has a couple of little wiggles in there. Okay? And then we talked about turning points, and we said, if you figure out the degree of a polynomial, the number of times it can turn back and forth is 1 less than the degree. So if I have an 8th degree polynomial, how many turning points can it have? Up to 7. Does it have to have 7? Nope, because there's an example right next door of something that has a degree 6. Whoops, let me slide that down. Here's a degree 6, and how many turning points does it have? Only 1. It only turns around once. Okay? So you want to make sure you're clear on that. It can have up to that many. It doesn't have to have that many. And then we talked about multiplicity of a 0. What did multiplicity help us figure out about the graph? Touches or crosses. Touches or crosses. That's Jeff Thompson, everybody. You got that one. So if it's odd, it crosses. If it's even, it just touches. And we went through an example right here. Okay, so we had x plus 2. The 0 is negative 2. Its multiplicity was 1. It's got to cross there because that's odd multiplicity. Even multiplicity here, we know it's going to touch. Odd multiplicity here, we know it's going to cross. So we made our graph look like this. It touches at 0. Is that right? Oh, I'm looking at this one down here. Okay. So here was example 7. Okay. The x-intercept is 0. Its multiplicity is 2, so it touches. The x-intercept is 2. Its multiplicity is 1, so it crosses. And it looks like, if you multiply those together, it looks like x cubed. So that's why it started down here and ended up here. Touch when you get to 0, cross when you get to 2, and there we go. And in fact, that one has 2 turning points. Okay, are there any questions? Then we went through and did this one right here that we had to factor and do stuff like that with. And we came up with this graph. And then we did example 10. We came up with a 5th degree polynomial that had those 4 zeros, one of which had a multiplicity of 2. So the x minus 3 was the only one that was squared. Okay? Raise your hand if you got started on the assignment on 4.2. Thank you very much to you 4 people. That's very nice. Okay. Go ahead and flip the page over. And I made some extra room. I should just increase the size of that one there. So I made some extra room. And you've got some problems on your assignment that are literally this simple. It just says, determine which functions are polynomials. Is that a polynomial? Yes. This? Yes. Parker says no. Anybody agree with Parker? You want to disagree with Parker? Corby disagrees. Josh disagrees. Jessica disagrees. Natalie. Okay. This one is a yes. It is a polynomial. Okay. Just because that's a fraction, it's the coefficient. Okay. It's okay to have a coefficient that's a fraction. This is not okay. Do you see the big difference between the two of these? This would be x to the first. Technically, this would be negative x to the negative 1. Can't have negative exponents in a polynomial. Okay, so this one here is a no. How about this one? See that right there? That's the problem. That is a square root of x cubed. Can't have any roots in a polynomial. Okay, so this one is a no. How about this one? Also a no for the same reason. How about this one? Maddie Gainey is shaking her head, and that's correct. Okay, this one is a no. Here's the problem. If we were to break this apart, everybody watch please, because this skill isn't used very much. If I did x squared over x cubed minus 5 over x cubed, if I were to cancel these two with those guys right here, I'd have 1 over x minus 5 over x cubed. So I've got two issues. I've got an x in the denominator here and an x in the denominator there. Not okay. How about this one? This one is a yes. Okay? If I were to multiply these together, x squared right here, because that's got a square on the outside, x squared right here, so that would be x to the 4th with a 2 in front of it. It would look like 2x to the 4th. Okay? Probably have some turning points and stuff like that. Okay? Next up, it says, use transformations of the graph of y equals x to the 4th, which looks like real steep, flat in the middle, or y equals x to the 5th, which looks like real steep, flat in the middle, and then go up, to graph each one of these. So what does that minus 2 do to this graph? Right 2. Remember, opposite of what you think. So we're going to take this graph and we're going to go 1, 2, and it's going to go like this. That point right there is 2, 0. Can I label a couple of other points on there? Over 1, up 1 to the 5th power. What's 1 to the 5th power? 1. So this is going to be 3, 1, and this is going to be 1, negative 1. Is that all right? Easy enough? Okay, would you do this one and label at least 3 points? Do this one and label at least 3 points. Is this a parabola? Does it look kind of like a parabola? A little bit. But it's definitely not a parabola. Okay, Lyle, take this shape, which kind of looks like a parabola, but it's a little steeper on the outside and flatter in the middle. And what are we going to do with it to make this shape? So left 2, down 3. So it's going to look something like this. And if I labeled 3 easy points, easiest one to label? We can call it a vertex. Say -2, -3. Okay? And what about this one right here? Good. And this one right here? Which coordinate do we know for sure without even thinking? It'd be, okay. Maybe you don't have to think as hard as I do. Okay? These are both on the same horizontal line, so they both have the same y coordinate because we've got that symmetry. Okay? We've got an axis of symmetry running down the middle. So if this one is -2 for a y coordinate, this one would be -2 for a y coordinate. Okay? And then -3. Very good. Any questions there? You've got some problems that just kind of ask you to do a couple transformations. Just basically know what those power functions look like. Okay? Again, if it's even, starts up here, ends up here. If it's odd, starts down here and ends up here. Okay? Unless we do a vertical flip or something like that. Okay? All right, now let's take a look at a couple that are more interesting. These are the type of problems that you're going to need. I apologize for not leaving you space. I'll do that in the future. If you grab a piece of paper, something that you can write on, that's what you're going to need here. This is the type of thing that you're going to be asked to do on the exam for this class. You can be almost guaranteed it's going to be on the final exam for this class also. And you're going to see it on a midterm exam and on the final exam for 1050. Almost guaranteed on the final exam for 1050. Okay? This is just classic college algebra stuff. So the first thing we want to do is list each real zero and its multiplicity. Determine whether it touches or crosses. Determine the behavior near each x-intercept. That you don't have to do. I'm fine with it just saying determine whether it touches or crosses. Determine the maximum number of turning points. Determine the end behavior. In other words, find the power function that it resembles. What word did I say, or what phrase did we say we were going to use instead of resembles? Looks like. What does it look like? What does it resemble? Okay? Now, can somebody tell me something nice about 46 and 47? What's that? They're already factored. They're already factored. Okay? So if they're already factored, then it's really easy to look at it and figure out what the zeros are. What's the zero that comes from here? -4. What's the zero that comes from here? -3. What's the multiplicity? 1 here, 3 here. Behavior. So touch. So we did this. Didn't we do this? T or C? They both cross. Okay? So if we've got a couple that touch and a couple that cross, you've got to be really careful, when you're actually doing the graphing. Let's see. Found each zero and its multiplicity. Determine whether it touches or crosses. Got that figured out. Maximum number of turning points. Well, to do that, what do we need to know? We need to know the end behavior. So it's almost better if we answer E before we answer D. So let's look through here. How many x's right here? 3. How many here? So I've got x to the 4th, and this looks like, careful here, what x to the 4th? 4x to the fourth. You should include that. Now, is 4 going to change x to the fourth that much? It's going to make it steeper. Okay? Graph's going to get really tall really fast, so it's going to be really steep. But does it change this behavior? X to the fourth starts up here and ends up here. Does it change that? It doesn't. What would need to be done here in order to change that? Yeah, we'd have to have a negative in front. So the big deal here is that it's a positive 4. That tells us we know we're looking at some shape like this. Okay? Starts up here and ends up here. Okay? Maximum number of turning points. Now, should I say there are 3, or should I say up to 3? Okay? There could be 3 turning points. Okay? So let's do this. 1, 2, 3, 4. 1, 2, 3. You with me? Okay, where does it start? Down here? Starts up here. What does it do when it gets close to -4? Does it pass through it, or does it touch it? Passes through. Okay, then it's got to turn around. When it gets to -3, what does it do? Crosses through. Okay? Now, that is a really crappy looking graph. Okay, Bree asked yesterday, how do you know how far down it goes? Do you want to pick a number between 3 and 4 to plug into that? Probably not. Okay? But we ought to at least add some other point on here. Notice I don't have a scale on the y-axis. Okay? Pretty hard to tell what it would look like. If I were really going to convince somebody that I know what I'm doing when I graph something, there's one other thing that we ought to put on here that really isn't very hard to find. What? The problem with this is we don't know whether it's symmetric, okay? Because if it comes down and does a big loop here and then another one like this, it may not be symmetric. Natalie, what is it? We need the y-intercept. You should always be able to find the y-intercept on a function, because what do you have to do to find the y-intercept? Plug in a 0. Now watch what happens when we plug in a 0. This is a 4. What's this? Careful. That whole thing is a 4. What's this? 3 cubed. Holy cow. It is a 3, isn't it? Okay. This is 16 times 27. It is pretty high up there. Does this look like I've got that probably about right? It's probably pretty darn steep. It goes way up there. At 3, think about this for a second while somebody's grabbing their calculator and typing in 16 times 27. At 3, we were right on the x-axis, sorry, -3. By the time we get to 0, Josh, what's the number? 432. So it's way up here, and we could label that as 0, 432. Now, if I put all of this stuff, if I've got all that stuff labeled, and I know what these points are here, if we kind of said -4, 0 and -3, 0. If I have those things that are highlighted in yellow, if that's what I put on my graph, is it pretty clear I know what I'm doing? Absolutely. Okay? That's what you need to be able to do. Okay? Could you do that with this one? Are there any x-intercepts that come from this guy? Does that ever equal 0? Think about it for a second. Plug in a number, get a positive, and then add 1 to it. Is it ever going to be 0? Never. Okay? And then take a look at this right here and see if you can figure out which one of these would work. Notice you can tell whether it touches or crosses, so you know whether each one of those would be odd or even as far as the multiplicity goes. Okay. If you've got questions about 4.2, make sure you work on it. We'll maybe have a quick minute or two to go over questions at the beginning of class tomorrow. But that's it. Have a great day.